So first of all, thank you for inviting me to give this talk at the thermal seminar. Today, I want to talk about a recent paper that we put out last November with David. Also, I should note that a lot of the relevant background of this talk is there in a previous paper by these authors. So if you're curious, you should definitely take a look. So in this paper, we explored what we call a genus-2 crossing equation, which arises from looking at the CFT partition function on the so-called the genus-2 manifold and expanded into different ways. Each expansion allows us to access different CFT data, and the equivalence of both sides give us some constraints. But these constraints are not independent from the usual 4-point crossings. Rather, you should think of this new genus-2 crossing equation as encapsulating infinitely many 4-point crossing equations, as is illustrated in this picture here. As a concrete application, we can use this genus-2 crossing equation to derive an asymptotic relation between heavy OP coefficients and thermal 1-point coefficients. Just to give you a flavor of what this relation looks like, I show on this slide a schematic form for 3D scalars. So let's unpack this formula a little bit. So on the left-hand side, we have rho 1, rho 2, rho 3, which denote the density of states for the corresponding conformal representations. And the C1, 2, 3 is the average OP coefficients. On the right-hand side, the first factor is going to be a sum over all the primaries of the 3D CFT, all the primaries of 3D CFT. And B sub O is a thermal 1-point coefficient, and Q sub J is just some known constant, which I will show in a later slide. Inside this exponential factor, F and C1 are theory-independent Wilson coefficients. And I will also explain what they mean later as well. This asymptotic relation is valid in the limit when delta 1, delta 2 goes to infinity with the same rate, and delta 3 goes to infinity faster than delta 1 and delta 2. But of course, in this first slide, I left out a lot of one-loop factors, and I kept things rather schematic. You don't have to worry about this. I will show you the full-fledged form of this OP asymptotic in the last slide. So here is a plan of the talk. The genus-2 crossing equation arises from two equivalent ways to decompose the genus-2 partition function into sum over states. So we'll start the talk by explaining what is a genus-2 manifold in higher dimension and how to parameterize the flat conformal structure on such manifold. Then I will try to write down the dumbbell channel decomposition and the sunrise channel decomposition of the genus-2 partition function. The so-called dumbbell channel and the sunrise channel, you should compare them to the S channel and the T channel for the 4-point correlators. So the full-fledged genus-2 crossing equation is relatively complicated. So as a first line of attack, we will focus on a special kinematic limit, which we call the thermal flat limit. And I will define this limit in the third section and explain how the crossing equation gets simplified. Finally, we derive the OP asymptotics using the simplified crossing equation. Okay, so let's start by explaining what is a genus-2 manifold in D greater than or equal to 2. So in D greater than or equal to 2, we define the genus-2 manifold as a connected sum of 2S1 times SD minus 1. If I have two deep dimensional manifold A and B, taking their connected sum basically means removing a d-dimensional ball from both A and B, then glue the boundary sphere together as illustrated in the right figure. And you can convince yourself that in 2D, this construction does reproduce a familiar genus-2 surface. So in a CFT, up to the existence of Weyl anomalies, the CFT partition functions or CFT observables more generally should depend only on the conformal structure of the underlying manifold. In this work, we will focus on metrics that are conformally flat. So our next task is to understand how to parameterize the conformal flat structures on a genus-2 manifolds. So to classify conformal flat structures or flat conformal structures on a particular manifold, it is often helpful to first understand how this manifold can be built out of more basic pieces. So for example, take the 4-punctured sphere as the simplest example. There were different ways of cutting it into 3-punctured spheres. In particular, I can divide the 4-punctured spheres into an upper hemisphere and a lower hemisphere, or I can divide it into a left and right hemisphere. Algebraically, if I insert a resolution of unity in the cutting sphere, then I will get the T-channel expansion and an S-channel expansion of the four-point correlation function. So similarly, for the genus-2 partition function, I can basically do the same, right? There are at least two different ways of cutting and gluing the genus-2 manifold into two three-punctured spheres. The first way is to build a genus-2 manifold by taking two copies of the flat space, remove three balls from each of them, and glue their boundaries with a cylinder. So in this construction, the flat conformal structure of the genus-2 manifold are determined by the gluing maps. I will call them G1, G2, and G3. The G1, G2, G3s are orientation reversing conformal transformations. But this parameterization suffers from some redundancies. So if you multiply all three of them simultaneously by the conformal transformation G or G prime, the conformal structure on M2 will be invariant because the simultaneous right or left action amounts to a coordinate transformation on the lower flat space or the upper flat space. So on the slide here, I should explain my notation on the slide here. On this slide, G denotes a d-dimensional conformal group, SOD plus 1, comma 1. And G minus 1 denotes orientation reversing component of OD plus 1, comma 1. In later sections, we will call this construction the sunrise channel. Now let's focus on the decomposition, which we call the dumbbell channel decomposition. So in the dumbbell channel decomposition, we can build the genus-2 manifold by gluing two one-punctured torus together. So we can take two three-punctured spheres, remove a ball from both of them, and glue the two tori. Sorry. So we can start from two three-punctured spheres and then build two one-punctured torus, and the flat conformal structures on the two one-punctured torus are parameterized by two conformal group elements, which we call GL and GR. And then what you can do is that you can basically glue the two tori together via some orientation reversing map, which we call GM. Again, we can perform like in the case of the sunrise channel, we can perform a coordinate transformation on the left tori and on the left tori and on the right tori independently without changing the overall conformal structure. And the effect is that we conjugate GL by some conformal transformation G, and then at the same time we conjugate GR by G prime, and then we multiply G middle by G on the left and G inverse on the right. So we call this construction the dumbbell channel decomposition. By the way, I should clarify at this point that the picture on the slide looks like they're in it looks like they're two-dimensional manifolds, but really you should think of them as living in D-dimension. In particular, the gray disks in each picture, they represent an SD minus 1 rather than a D2. So from both of these constructions, we see that the dimension of the moduli space, by moduli space, I mean the moduli space of flat conformal structure, is the same as the dimension of the conformal group. So in 1D, the genus-2 partition function will depend on 3 cross ratios, and in 3D, it will depend on 10 independent cross ratios. Okay, so far we've established the flat conformal structure on M. We've established the fact that a flat conformal structure on an M2 is determined by a triplet of conformal group elements up to some equivalence relations that I show here. But for the purpose of doing concrete calculations, we want to work with explicit representatives. Just like in the case of a 4-point correlation functions, we always want to restrict to a specific conformal frame. So let's see. I want to elaborate on how we can choose a conformal frame in the dumbbell channel and in the sunrise channel. So let me start by the choice of representative in the sunrise channel. It looks a little bit complicated, but it's actually very intuitive. So maybe let me start by explaining all the symbols on this slide. So capital I here in the expression of G1, G2, G3 basically represent inversion, and H1, H2, H3 are SOD elements. Here A1, A2, and the parameter beta 3, they're all real parameters. Now, this choice of Gaussian map have a very clear geometric picture, which is illustrated in the picture on the right. So basically, if you take two flat space and remove a ball centered at 1 plus A1, with radius being 1 minus, sorry, you remove a ball centered at 1 plus A2, with radius 1 minus A2, and then remove another ball centered at minus 1 minus A1, and the radius of this ball is 1 minus A1. Then you remove a third ball centered at infinity with radius 2. Then these three balls correspond to the three circles on the top. And you can do the same to the other copy of the flat space, and then glue the two larger spheres by cylinder with length beta 3. So you're supposed to think of the length of the larger cylinder as having length beta 3. And then glue the other two smaller spheres by a cylinder with length 0. It's a little bit hard to draw it is a little bit hard to draw a cylinder with length 0 in this picture, but it should be clear from the definition of all the parameters here. So this choice of frame has of course has some residual redundancies. That is, if you simultaneously multiply the three angular twists H1, H2, and H3 by elements in an SOD-1 subgroup, then it leaves the conformal structure invariant. We choose to leave this redundancy unfixed because the SOD-1 symmetry becomes important in later calculations. Okay, and we can basically do the same for the dumbbell channel. Let me explain the geometric picture behind it. So to start, we build a periodically identified annulus by gluing a sphere. Let's look at the right picture here. We glue a sphere with radius e to the power minus beta r over 2r with concentric sphere with whose radius is e to the power beta r over 2r times r. And then, of course, the distance between the inner and outer sphere is going to be 2r times sinh beta r over 2r. Then you can remove a unit ball centered at radius r and do the same for the other torus on the left. And then glue the boundary of the two removed ball with a cylinder, and the length of the cylinder is supposed to be beta. Of course, you can apply some angular twist along the annulus and also apply some angular twist along the cylinder in the middle. All the angular twist, HL, HM, and HR will be similarly subject to some remaining residue equivalence relationships. So at this point, you might wonder why should I choose such a strange geometry? To jump ahead a little bit, later when we take the thermal flat limit, what we will do is that we'll basically set R to infinity. So from this picture, you can already see that in the R goes to infinity limit, the radius of the two tori will blow up. All right, so the two SD-1 will become flat space. But the distance between the inner sphere and the outer sphere will become beta L and beta R, which remains finite. So in this limit, if you take the R goes to infinity limit in this picture, what you'll end up having is a H shape with the cylinder with length beta connecting two very thin cylinders on the left and on the right. Okay, so that finished the discussion of the representative geometry in both channels. What you can do next is what I want to explain next is to write down the dumbbell channel decomposition of the genus-2 partition function and the sunrise channel decomposition of the genus-2 partition function. So basically, what we do is we insert resolution of identity in the three colored circles here. So for the left torus, when we supply it with a ket, then then we end up with a torus one point function multiplied by a torus partition function z s1 times sd minus 1. And the same is true for the right torus. In the meantime, if the intermediate operator we sum over transforms non-trivially under SOD, then it will be sensitive to the action of HM. Now, perhaps in this formula, I should explain a little bit what does the factor Z glue means. So the factor Z, so whenever we glue a cylinder onto a plane or onto an annulus, the metric might not be smooth at the junction where the cylinder meets the plane on the annulus. So we will capture this non-smoothness by adding this extra factor Z glue. But this gluing factor is not too important because in this work, we essentially focus on 3D, and in all dimensions, there will be no violent anomaly, and therefore the junction factors from the dumbbell channel will essentially cancel with the junction factors from the sunrise channel. Okay, so this is basically the idea behind the dumbbell channel decomposition of the genus-2 partition function. Similarly, we can write down an expansion in the sunrise channel. Well, in this case, each triplet of state will give us. So you should think of supplying a resolution of identity in each triplet of resolution of identity at the three colored spheres here, and then each of this. Well, the three-punctured sphere on the two three-punctured spheres will basically give us a pair of three-point functions. For each terminus in this triple sum, we can factor out the OP coefficients from the two three-point functions, and then the rest is basically a purely kinematic object. And we call this kinematic object the genus-2 block. All right, so at this point, are there any questions? Okay, if not, I should probably proceed. So I've introduced two sets of coordinates on the moduli space, right? We have the sunrise channel coordinates where we have the A's and the betas and the H1, H2, H3s. And then we also have the dumbbell channel coordinates, which is beta L, beta R, and also the angular fugacity. The next immediate question is, how do you match the two sets of coordinates, which are supposed to cover the same moduli space? Here is the idea. Abstractly, each channel gives us, sunrise channel and the dumbbell channel give us a homomorphism from the fundamental group of the genus-2 manifold to the conformal group by assigning conformal transformations to different cutting spheres and then concatenate them. Suppose the two homomorphisms, if the two homomorphisms give rise to the same conformal structure, then for any element in the conformal group, in the fundamental group, its image under these two homomorphisms must be conjugate. So in practice, we will commit to a specific representation of the conformal group that compute products of the matrices from both channels and then match their characters. If this is too abstract, it's okay. Let me give you a concrete example. So consider the following three loops on the genus-2 manifold. We call the red loop A, the blue loop will denote as loop B, and the green loop is basically B times B concatenated with A. Now, in the dumbbell channel, we see that the loop A first goes through the cutting sphere corresponding to GM, then it goes through GL inverse, and then it comes back through GM inverse. So phi D will map the loop A to GM inverse, GL inverse, GM. Similarly, it maps the loop B to GM. Sorry, it maps the loop B to GR, right? And then in the sunrise channel parameterization, this loop A first goes through G1 inverse and it comes back through G3. So phi S will map A to the element G1 inverse G3, and similarly it maps B to G3 inverse G2. And I suppose we work in 1D, and we want to match the sunrise channel decomposition with we want to match the sunrise coordinates with the dumbbell channel coordinates. What we need to do is to choose a representation. So let's work with a vector representation, compute different products of the matrices, and then basically match the traces. As you can see in the example here, even in 1D, solving for the exact relation between A1, A2, beta 3, and beta L, beta R, beta is already a bit complicated. But you don't have to worry about it because like later, we're only worried about matching two sides. So we'll basically try to solve the matching between two sides in a 1/r expansion. And R is the parameter that is supposed to go to infinity in the thermal flat limit. Okay, so finally, we're ready to discuss the thermal flat limit. As I mentioned before, the thermal flat limit is defined as a limit where R goes to infinity. But in addition to that, we want to turn off all the angular vigacities just for simplicity. So in the dumbbell channel, as we already discussed before, the two torus on both sides will basically blow up to become cylinders. And therefore the torus one-point function will simplify. For example, we know that for scalar primary, the cylinder one-point function is fixed up to a one-point coefficient BO. So for this reason, in the thermal flat limit, the dumbbell channel decomposition will look much simpler. The dumbbell expansion now takes a much simpler form, which we list on the right-hand side. So let me mention that when we take a sum over operators, only scalar and symmetric traceless tensor primaries will contribute because essentially these are the only operators that can have non-zero cylinder one-point functions. And let me also note here that C sub O is a norm of state for the primary state O, and Qj is just some known factor which is expressed as some quotients of gamma functions. All kinematic parameters appear in the sum. All the kinematic parameters, beta and beta L, they will appear in the sum via this combination e to the power minus beta over beta L times beta R. So the three betas cannot be as small as possible, basically, because if you want to be able to like drill out a unit ball from a cylinder, that cylinder cannot be as thin as possible. So therefore, beta L and beta R must be greater than or equal to 2. And since beta is greater than 0, then this whole combination sits within the interval 0 to 1/4. Now, as R goes to infinity, the entire sum remains fixed, but the two torus partition functions will grow with R, and eventually it becomes infinite. But the torus partition function goes to infinity in a controlled way, and the growth is controlled by the thermal effective action. So are there any questions at this point?
So just to understand,
Yes.
so now this is the expansion, like if you want the thermal hotspot expansion of the partition function only for the dumbbell.
Sure.
This one is
Right.
only for
This
the
is the
dumbbell.
expansion. Yeah, this expansion is only in the dumbbell channel. And you mentioned the fact thermal hotspot, but like I wanted to clarify that we haven't used any hotspot conjecture in this
Okay, okay, okay. Yeah, maybe I just expressed
in this
myself
expansion.
using this, but you didn't say, you never said it.
Yeah,
Okay, okay. And I imagine that for the sunrise, there will be something analogous.
yes. So for the
Okay, okay.
sunrise, yeah, I'll explain a bit. I will explain a little bit. Basically, in the sunrise channel, you have the genus-2 block, and then in the thermal flat limit, you will restrict to a particular asymptotic form for this genus-2 block because you care about this thermal flat limit, and that
Okay,
leads to
okay.
some simplifications.
And maybe just very, very final, very quick question. Like, no, I understand
Yeah,
that
yeah,
beta L and beta R are the two temperatures of the two different circles that you
yeah.
identify.
Right. Beta.
While
Yes.
beta, without any labels, I missed the explanation of beta without labels.
Ah, okay. Let me go back to this picture. So I think it should be
Okay,
clear from
okay,
this
okay,
picture.
okay, okay, okay. Got it, got it, got it. Okay, thank you.
Okay, great. Yeah, thanks for the question. Yeah, if there's no other question, let me probably give like a very quick review of thermal-effective theory. So, so if you consider a CFT defined on a torus, by torus I mean S1 times SD minus 1. Here the subscript beta omega A means I'm gluing the two spheres on the two ends of the cylinder by some angular twist. The angular fugacity is given by beta times omega. And now, so consider a CFT defined on such a space. Now, dimensionally reduce d-dimensional CFT on the thermal circle. Typically, you will end up with some quantum field theory in a d-1 dimensional sphere, and we typically expect that quantum field theory to be a gapped quantum field theory. So for a gapped quantum field theory, you can write down a partition function using the the background field. Here, in this context, we have a d-1 dimensional background metric, a KK gauge field, and a dilaton field. And all these background fields can be read off from the d-dimensional metric, and therefore depends on the geometric parameters such as beta, r, and omega a. Now what I can do is to adopt the EFT method and then write down all possible local terms allowed by symmetry. Now I can sort these terms according to their derivative order. For example, at leading order, I always have a cosmological constant term, which have derivative order 0. Then I have the Einstein term and Maxwell term, which have derivative order 2. Each term is going to be paired with a Wilson coefficient, and the precise value of this Wilson coefficient depends on the theory. So, for example, if you focus on 2D CFTs, then essentially the only Wilson coefficient you will have is this f, which is paired with a cosmological constant term, and that f is proportional to the central chart of the theory. Now, after evaluating, but of course, this formalism also generalizes to higher dimensions. So if you evaluate the d-1 dimensional integral of the sphere, you will end up with an R expansion as shown in the last line. And this R expansion gives the leading singular behavior of the torus partition function as we send R to infinity. So, okay, so that is a one-slide summary of the idea of thermal effective theory and how you should control the infinity from the dumbbell channel. Now let's maybe switch gears and then talk about what happens in the sunrise channel. So we already know how the dumbbell channel coordinates behave in the flat limits. And then what we can do is to adopt the matching procedure explained earlier and then solve for the sunrise channel coordinates order by order. As you can see here in the thermal flat limit, A1 and A2 remains order 1 and beta 3 scales towards 0 because it has this 1 over R squared here. Now, why do I care about this? Why do I care about the scaling of these parameters? Well, this is because in the sunrise channel, the genus-2 blocks are functions of the 3 A's and the betas. In the thermal flat limit, we care about the asymptotic form of the genus-2 block when beta 3 goes to 0 and A1, A2 remains finite. right? So in the thermal flat limit, we have our simplified crossing equation, where on the left-hand side, we have a sum over squared OP coefficients multiplied by a genus-2 block. It might look like nothing happens, no simplification happens here, but what you should keep in mind is that this B123 is actually an asymptotic form in a particular scaling limit. Here, the superscript S and S prime are labels for tensor structures. On the right-hand side, we have three factors. The genus-2 block satisfy. Sorry, the three factors are like the first of all the sum over primaries, the sum over scalar primaries, and the symmetric tracelet primaries, and also the two torus partition functions. It is known that the genus-2 blocks satisfy an orthogonality relation. So what we can do is we can just use this orthogonality relation to invert this whole sum on the left and then extract the squared OP coefficient, which brings us to the last section of my talk, which is to use the genus-2 crossing equation in the thermal flat limit to extract heavy OP asymptotics. And of course, this is in relation to the thermal 1-point coefficients. To do that, the main computation you have to do is to evaluate this inversion integral. Let me maybe unpack things a little bit. So to perform this inversion integral, the integral measure is a measure over the moduli space of flat conformal structures. We can adopt a Faddeev-Popov procedure to fix the gauge and express this measure in terms of the sunrise channel coordinates, which are A1, A2, beta 3, together with all the angular fugacities. But of course, we want to supply an additional Faddeev-Popov determinant. Now, for the genus-2 partition function, what we want to do is we want to expand it using the dumbbell channel expansions, which we also explained in the previous slide. For the genus-2 block, we want to compute it using the shadow formalism. And hopefully, if I have the time, I will explain a little bit later how to evaluate it using shadow formalism. This whole computation is probably a bit technical. I'm not going to burden you with all the technical details going into this computation. So instead, what I want to do is I want to comment on a few tricks we use in the course of this calculation, which I think is interesting and probably is also transferable to other contexts. So the inversion integral, of course, is too complicated to compute exactly. So we will be using a lot of saddle point approximations. And we are making the following assumption, which is that the one sentence summary is that we are treating the thermal flat limit basically like some kind of thermodynamic limit. What this means concretely is that first of all, we assume in the sunrise channel expansion, when we sum over a triplet of states, the sum is dominated by a saddle point located at delta I star, lambda I star. Second of all, when we compute the inversion integral, we need to first fix the choice of delta 1, delta 2, delta 3. Now, if we choose them so that the external deltas are comparable with the saddle's delta I star, then as we integrate over the moduli, the integrand also develops a saddle point, and this saddle point is within the thermal flat limit. Probably a helpful mental model is to just compare the genus-2 partition function as a canonical ensemble partition function, right? Then the sunrise channel decomposition is analogous to a sum over energy levels, and typically what happens is that as rho of E, which is the density of states, rho of E grows with energy, but the Boltzmann factor decreases, and the combination of the two factors will give rise to a saddle point. As you go to the thermodynamic limit, the saddle point becomes sharper and sharper. So eventually it suffices to just look at what happens near the saddle point. And then you should compare basically this rho of E with the squares of the OP coefficient. And you should compare the Boltzmann factor with the genus-2 block. Now the inversion integral is like an inverse Laplace transform, and we know that the saddle point of the inverse Laplace transform is compatible with the saddle in energy. So for the calculation, it is then important to know where the saddle delta I star and lambda I star is. One way to do this is to compute expectation values of various Casimir operators. We know that the genus-2 blocks are defined to be simultaneous eigenfunctions of the three Casimirs. This superscript I means that it can act on different places. So the expectation value, so the expectation value of the Casimir, we define it as basically the action of the Casimir differential operator on the genus-2 partition function divided by the partition function itself, which is a very this is a very natural definition. Now, if we plug in the sunrise channel decomposition and then assume that this decomposition is dominated by the saddle point, then moments of the Casimir will just give you polynomials of delta I star. Right. On the other hand, we can compute this Casimir moments using the dumbbell channel expression. The dumbbell channel decomposition contains a factor h of z. The h of z is the, sorry, I should mention that h of z is basically the sum of thermal one-point coefficient squared, and we know that this sum remains order 1 in the thermal flat limit, and all the leading order contribution only comes from the two torus partition functions. So using this dumbbell channel expression, we can explicitly evaluate the Casimir expectation values. But to give you a feel of how this trick works in practice, here are the Casimir expectation values in 3D. Now, if we take the square root of the quadratic Casimir, you will get the leading term in delta star. We see here that delta 1 star, delta 2 star scale as r cubed, but delta 3 grows faster and it scales at r to the power 4th. That explains why in the OP asymptotics there is this scale separation. We've also computed the first moment of the quadratic Casimir. Notice that the quadratic Casimirs are just squares of the quadratic Casimir, which means that the saddle point in spin is parametrically finite. Actually, the saddle in spin must be 0 for a symmetry reason. Are there questions regarding this? Okay, if not, I prepared some slides to explain the shadow formalism and how to compute the genus-2 block, but I think at this point it feels probably overwhelmingly technical. So maybe let me just jump directly to the final results, and if you have questions, we can come back to it. So as I promised in the beginning of the talk, here is the full flat form of the OP asymptotic. So maybe I should unpack the right-hand side a little bit. So this T tensor is basically a product of two three-point structures. And the dimension of lambda i's are dimensions of the, well, we're assuming that the three operators are in dimension lambda 1, sorry, transform as lambda 1, lambda 2, lambda 3 under SOD. And this is basically the full-fledged form of the OP asymptotics. So I should also mention that this OP asymptotic formula is only valid as we send all the lambda i's to infinity with quotients with lambda 1 and lambda 2 growing at roughly the same velocity, but delta 3 should grow faster so that this whole quotient is held fixed. And also, this formula is not only valid for scalar primaries, it's also valid for spinning primaries as long as the spins are kept finite. Okay, so are there questions, or should I proceed with discussions?
So here, like,
Huh?
so here, like, you are considering. So should I read this as some kind of sum rule for the b squared, the 1-point function b squared?
Yeah, I wouldn't say it's not an exact sum rule, because usually when you say sum rule, I'm expecting something that is like an exact equality, but in this case it's an asymptotic relation. So the right-hand side has a lot of subleading corrections in
Right.
1 over r.
Yeah. Right.
But yeah, it's right that, so the way to read it is that you can think of this as relating two sets of data of a CFT. The left-hand side, you have heavy OP coefficients. On the right-hand side, you have all the thermal 1-point coefficients. But
Right.
of course, you can raise this complaint that what am I really learning about a CFT through this crossing equation? Now, here's one thing you can do. Notice that I commented earlier that this asymptotic relation is valid when this quotient delta 1 squared, delta 2 squared divided by delta 3 cubed is held fixed, right? So what you can do is to choose a quotient, choose such delta 1, delta 2, delta 3, so that this quotient is relatively small.
Okay.
So basically, this asymptotic, imagine the space of delta 1, delta 2, delta 3, the three axes of delta 1, delta 2, delta 3, then this formula is valid when you travel together, when you travel along certain rays in this space as you approach infinity, right? Now you can choose a particular family of such rays in the delta space so that this quotient is very small. Then if you go along such rays in the delta space, then you can essentially just focus on the first two terms in the sum. And for example, you're justified to just, if this quotient is small enough, then you're justified to just focus on the contribution of the identity. Then you're really learning something new about heavy OP coefficients.
I see.
Does this make sense?
Okay. Yeah. Yeah, I see. So choosing different delta 1, delta 2, delta 3, I can
Yeah,
like
yes.
yeah, this is the game. Okay, I understand. Thank you.
All right, maybe let me proceed with some discussions of future directions. So for high-dimensional CFTs, there has been many previous papers on heavy OP limits, heavy OP asymptotics, using the method of either thermal EFT, hydrodynamics, or 6-point crossing equations. All these different approaches probe different limits, and some of them are overlapping. But so far, it is not clear to me how I should relate them or how to interpolate between different scaling limits. It would be really nice if we can understand this problem, but perhaps a more humble first step towards this goal is to check some of these predictions explicitly in free theory. And this is something I'm trying to do currently. I'm just trying to enumerate a lot of like very heavy primaries and try to compute the OP coefficients and also their thermal 1-point coefficients by doing a lot of explicit weight contractions, and hope that we can verify some of this EFT typed predictions. But other interesting directions include, for example, in this work, we only focus on the case where all angular fugacities are turned off. It would also be interesting to consider what happens when we turn on some angular fugacities in the geometry. In that case, we'll be able to extract OP asymptotics with very large spin. But of course, more ambitiously, after we are able to very efficiently compute the genus-2 blocks, eventually we should try to feed this genus-2 crossing equation to SDPB and see if we can extract interesting numerical bounds. Yeah, I think this should conclude the content of my talk today.